we have been talking about the data link layer so far. One of the confusions that people have with the data link layer, and I will clean that up right now, is let's say you have a switch. Let's call this switch 1, as always. And you have two PCs connected to the switch. PC 1 and PC 2. And we're not going to worry about the ports they're connected on. Now, earlier I said that the data link layer deals with transmission over the local data link, which means the link between two devices, two directly connected devices. Now, people take that to mean that this link between PC 1 and switch 1 is one data link. No, that is incorrect. The switch itself is one data link. So, when you draw the switch out in a diagram, that is considered a physical diagram. In a logical diagram, I would draw the same topology as such, PC1 and PC2. And it is assumed that there is a switch in the middle because you really can't buy a wire at Best Buy that looks like that. So, a switch is one data link. Everybody connected to that switch, all PCs or devices that are connected to that switch are on the same data link. So this link between switch 1 and PC 1, no, that's not a data link. The link between PC 1 and PC 2 is the same data link. Which is why the whole function of a switch and the process that I described earlier on how a switch operates is called transparent bridging. So a switch is nothing more than a bridge between PC 1 and PC 2, and from the point of view of these PCs, it is transparent to them. It doesn't exist. So in a logical topology, you will draw out the PCs or the end devices connected to the switch, but not the switch itself. Now, having said that, we can move on to the concept of broadcast and collision domains. So first, a broadcast domain. What is a broadcast domain? Well, a broadcast domain is the area of a network where a broadcast will spread out to if sent by one device. So let's say you have a switch with a bunch of PCs connected to it, and one PC sends out a broadcast frame. Remember, the broadcast frame being one with all Fs in the destination portion of the frame. How far will that broadcast sent by one PC spread out to? So by default, all switches, or all Cisco switches, are one broadcast domain. So if you have a switch, it is one whole broadcast domain by default. Routers, on the other hand, break up broadcast domains. So a broadcast cannot transverse a router. So let's say you have a router, the R denoting a router, and you have a switch attached, and some PC, let's call it PC1, sends out a broadcast frame. That frame will reach the router, and the router will drop it. By default, this broadcast cannot transverse, go across a router. So routers break up broadcast domains. A switch is one big broadcast domain in itself. And of course, a hub always floods, so a hub is one big broadcast domain too. Now, collision domains. Collision domains are areas of the network where if two devices transmit at the same time and they are running half duplex Ethernet, and if they are running half duplex Ethernet and both devices transmit at the same time, the frames that those devices send can collide. So a collision domain is an area of the network where collisions can occur. Now, each port on a router and each port on a switch is its own collision domain. So once again, each port on a switch and each port on a router is its own collision domain. A hub is one big collision domain. So a hub is one big collision domain, one big broadcast domain. A switch is one big broadcast domain. And each port on a switch and a router is its own collision domain. Now, collisions can only happen when you're running half duplex Ethernet. Before I draw the diagram for broadcast and collision domains, I have to explain what Ethernet is. Ethernet is a layer 2 protocol that runs at 10 megabits per second, half duplex. So the speed is 10 megabits per second, and it runs at half duplex with something called CSMACD, which stands for Carrier Sense Multiple Access with Collision Detection. So first, let me take care of the duplex part of it. Ethernet runs at half duplex. Half duplex means that bidirectional communication is possible, but only in one direction at a time. And as an example, you can think of a walkie-talkie. With a walkie-talkie, only one person can be talking at a time. Both people can't talk at the same time. Full duplex, in opposition, means bidirectional communication is possible. You can transmit both ways and simultaneously, which is at the same time. And you can think of that as a phone conversation. And then you have simplex, which is only unidirectional communication, but not part of CCNA. The CSMACD part, or Carrier Sense Multiple Access with Collision Detection part, when you're running half duplex Ethernet and two devices transmit at the same time, when it's not allowed, the frames can collide. And when this collision happens, CSMACD is constantly listening in on the wire. And when CSMACD, which is built into half duplex Ethernet, hears a collision, it sends out a jamming signal to all the devices. And it asks all the devices to stop transmitting for a randomized time period. So let's say if there are 4 devices and one of them gets told to stop transmitting for 10 milliseconds, and another one gets told to stop transmitting for 50, and a third one for 12, and a fourth one for 100 milliseconds. When they try to retransmit, the chances are lessened that they will retransmit at the same time, and hence the collision avoidance comes in. Hence the name Carrier Sense Multiple Access. Carrier Sense, I'm listening to the wire. Multiple access, more than 2 people can be on the media or on a switch at the same time with collision detection. Now, I've said that each port on a switch is its own collision domain. So, is that true nowadays? No, because ports on a switch by default run in full duplex mode. So in full duplex Ethernet, bidirectional communication can happen at the same time. You don't need CSMACD. 2 devices can transmit at the same time and collisions won't happen. However, since each port on a switch is its own collision domain, if a company does not have the money to spend and they do something like this, they put a hub on one of the switch ports and then they put a bunch of PCs on this hub. Hubs by default are half duplex. Then you're going to have a bunch of collisions when these PCs try to transmit through the hub. So each port is its own collision domain. However, if you connect the hub to one of the ports, of course, the devices connected to the hub will have collisions. Now, I have seen, such a diagram or such a question being asked on the CCNA exam, so I'm going to go through it real quick. So let's say we have 4 PCs attached to the switch, and then you have a router, and then you have a hub on this end, and you have 2 PCs attached to this hub. We'll make them PC4 and PC5. Now the question would be, how many broadcast and collision domains are in this topology, or this network diagram? Topology being synonymous with network diagram. Well, since I said each port on a switch is its own collision domain, and each port on a router, each Ethernet port on a router is its own collision domain, we have one collision domain here, 1, then the 4 ports that are connected to the PCs, 2, 3, 4, 5, and then this side, since it has a hub, is one big collision domain. So we have 6 collision domains. How about broadcast domains? Well, let's say PC2 sends a broadcast out. How far will that broadcast spread? PC1, 3, and 4 will get that broadcast, and the router will get hit with that broadcast, but the router will not allow it to transverse. So you have one collision broadcast domain on this side. You have one broadcast domain on my left-hand side of the router, and then one broadcast domain on the right-hand side of the router. So in this topology, you have two broadcast domains by default. Remember, I keep saying by default, and that's for a reason.